Hey, let's talk about vectors. So we're going to do three things with vectors. The first thing we're going to do is we're going to break them into their components. Break them down. Then we're going to combine components together. Combine components together. And then we're going to add vectors. All right. Now each of these steps is pretty easy in and of itself. So let's get started. The first thing, I'm going to break down a vector. Well, we know a vector is just a measurement with a direction. So we can represent that with an arrow. So here is my vector. This could be a distance that I walked. I'm going to call it R for the time being. All right. And I'm going to put a little angle down here. We'll make that theta. And for the sake of having values, let's say that R equals 10 meters and theta equals 30 degrees. 30 degrees. All right, so I now have this vector to say, well, I need to walk 10 meters, 30 degrees north of east, or y of x. Well, that's kind of hard to work with. It's hard to add. It's hard to think about. It's easier to think about go east for so many steps and then go north for so many steps. So we're going to change this into two different components. If you think about this as a trip, you can say, well, here's your starting point. There's where you start. And here's your ending point. Here's where you end. Well, there's more than one way to get from here to there. You could, if you wanted, go down around this big curly direction, but that's way more complicated. You could also, though, just take two straight paths. So say you wanted to go down like this and then back up like that. That'll also get you there. But again, a little bit complicated. So let's simplify it a little bit more. And what we're going to do is we're going to change this into coordinates that we're used to working with. We like working in the x and y direction. They're pretty convenient. So I'm going to draw two arrows. One that goes perfectly horizontal. Let's call this Rx. And then one that is perfectly vertical. Let's call this Ry. So this is the y component of R. This is the x component of R. These are at 90 degrees. So if you told me to go on a 10-meter trip at 30 degrees above the horizon or north of east or y of x, I could say, well, that's the same as walking over a certain way, making a left turn, and then walking up a certain amount. But I want to figure out what these values actually are. So we'll do another step. And the first thing we're going to do is put an equal sign here. So Rx comes from R. If this is longer, this is bigger. So it has a direct relationship with R. Now what we have to do, though, is scale it the right way. Fortunately for us, many mathematicians over the course of history had developed this system called trigonometry, and they've come up with these things called the trig function, sine, cosine, tangent, cotangent, secant, cosecant, all these great functions that do a lot of the work for us. So we don't really need to do anything more than utilize the right function. So when you have an angle, and you want to learn about the thing adjacent to the angle, next to it on a right triangle, we're going to use the cosine function. So if I said R times cosine of this angle, it's going to give me the projection of R onto the x-axis. Another way to think about this is imagine a person up here looking straight down at this big arrow. Well, if this arrow were to make a shadow on a wall over here, the shadow would be that big. Likewise, if a person were standing over on this side, they were standing over to the left and looking over this way, this arrow would make a shadow on a wall over here this big. So we have Rx is R cosine theta, and Ry similarly is R times sine of theta. So if I know R and I know theta, I can break it into these two pieces, and lets me think about the vector a little differently. Now, let's do the next step. Let's try to combine them. What if instead of having the vector, I have these two components? If Ry equals, say, 15 meters, and you have Rx equals, let's say, 7 meters. Well, again, we have a trip. Here's where I start. Here's where I end. Now, I could go this way, but that's not the fastest path. The fastest path between 2 points is a straight line, there to there. So now I want to combine them together. Well, if I just draw this line on there and call it R, and I remind myself that X and Y are perpendicular to each other, you can say, well, hey, this is a triangle, and it's a right triangle, so that means the Pythagorean theorem applies. This is C part of the triangle, call that A and B. Pythagorean theorem is C squared equals A squared plus B squared. Or, if I take the square root of both sides, C equals the square root of A squared plus B squared. So in that case, R equals the square root of Rx squared plus Ry squared. Pretty straightforward. Now, to really know about this vector, though, I also want to know this angle. All right. Well, just like we have sine and cosine functions, we have another function called tangent. And the tangent function says, if you give me an angle, I will give you a ratio of y to x. We have a y value, we have an x value. So it looks like we can use the tangent function. If we put in y and x, we can solve for this thing. The problem is with trig functions, they work one way. For tangent, I put theta in, and I get a ratio out. But if I have the ratio and I want to get theta, I need actually the opposite function. So instead of tan, we're going to use tan inverse. And that says, give me the ratio of y to x, and I'll give you theta. And again, this work is done for us. This is a function that's in your calculator, on your computer, on your smartphone. All we need to understand is that this is a system that helps compare ratios of sides of a triangle to the angles and to the hypotenuse. So we can use this function and say theta is going to be equal to the tan inverse of y, so ry over rx. Now we combine two components to get a vector. Now the last thing we're going to do is add them. And for this first example, we're going to use a pretty simple system. Let's assume that I have, let's do two. Let's say I have this trip where I go over 3 meters in the x, then I go up 2 meters in the y, and I go over 3 meters again in the x. Well, my starting point is here, my ending point is here. I could draw this again, and it might be better to draw it like this. What if I said 3 meters, and then another 3 meters, and then 2 meters? Same thing, same net result, start there, end there. But now it looks like two sides of a triangle. So I end up setting myself up to combine these components to get my R value again. Now I can add these two right in a row. If I walk 3 meters east and then another 3 meters east, I've walked 6 meters east. That's pretty straightforward. The problem we run into is, one, if you were to say, add this vector plus this vector. So we'll call this R1, theta 1, and R2, theta 2. That becomes a little bit tougher. So first thing we're going to do is we're going to try to put these together in a pattern that's a little bit easier to see. So, and forgive me, I'm starting running out of space. Here's R1, and then here's R2, R1, R2. Well, from breaking down components or breaking down vectors, we know we can split these up and say, well, R1 is really R1x and R1y. Y. And R2 is really R2x and R2y. So if we can break down into the components, well, then we can do what we did here and just